Hello? Hello? Okay, so good morning, everyone. Let's start our lab today. And today is about Lab 5, K nearest neighbors, which we talked about during the lectures last week. And please first download the lab script from the week 6 in OLE. And also there's another data set called data.txt. We'll use these two files today. Okay, so today we are going to train a KN model and try to introduce something about normalization that we've talked, I think, in the second lecture. And then we are still using the train test split to split the data set. And after that, we'll tune the key value for the KN model and then visualize the results. And in the end, we'll talk about the performance matrix related to the precision, recall, and F1 score. Yeah, so this is the main content today for this lab. Okay, so let's start from the part 1. Let me enlarge the page. Okay. So at the beginning, as usual, we should first import the packages, the libraries that we are going to use today. And as usual, we need to load the data set. So please first upload the data set on the workspace here, okay, the files here. You can just click this button, upload to session storage, and then load the data here that you downloaded from OLE. Okay, and then still we are using this read CSV method to read this txt file. And we just put the name of the txt file here. Oh, let's first have a look at the txt file. Yeah. Maybe it's better if I open this window. So in this data, in total we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 columns. We have 13 columns. The last column is the class or the category. It should be 0 or 1. Okay, it should be 1 or 0. And then the first column is the index. So this is the order of the instance, like the samples, the number of the samples. 1, 2, 3, 4, 5. And we have in total, yeah, 1,000 samples here. From 0 to 999, we have in total 1,000 samples. And the middle columns are all the features. But we don't know what the feature means. Okay. So the difference with the data set we used in the previous lab is that we have an index at the first column. Okay. So we need to deal with this index. So what we do here is that we put index. There should be an option in the arguments, okay, called index column. So we can define the index column. Let's say we put the first column. So the first column is the 0 column, okay? So we put the first column as the index. As we've seen here, the first column is the index, 0 to 999. Okay? And then if you still remember that we also have an argument of header, but this time header is not necessary to define because we have header. Last time we used header as none. That is because we don't have header in the file, but this time in the CSV or the TXT file, we already have header included. So we should put it as 0. And by default, it is 0. So even you don't define it, there's no problem. Okay, but just to mention this header, I put the header here. Okay, and then we print the data out. So again, if we delete the head, saying, oh, okay. So the head print the first 5 rows of the data, okay? The first 5 rows. When you put the head here, dot head, it means the first 5 rows of the data frame. So if you still remember that when we are using read file method, we save or we load the data into a data frame. And we use this head method to read the first 5 rows just to see what the data looks like. And then we can see here the features here, and then the target class, which is 0 and 1. Okay. And then the next step we should do is to normalize the data. So I've talked about it in the second lecture because all the features are in different scales. So it's not fair to directly use them because some feature might have very small values and some features might have very big values. So it's like when you are taking IELTS test or TOEFL test, right? Like the total score of IELTS is like 8, but TOEFL is like 120, right? So it's not fair to compare the score directly. You need to normalize by the mean and max value, okay? And like in this case, like IELTS test, so the mean is 0. The mean score you can get is 0. The max score you can get is 8. So you use this 0 and 8 to normalize, to scale this data into 0 to 1. Okay, so it's just like you divided this data by the scale of the range of the data. So let's say in the else test, the range of the data is 0 to 8. So the range is 8. And then when you normalize your else score by 8, and when you get a full score of 8, then the data will be 1 because you divide 8 by 8, by maximum value 8. And then if you got only 1 score in else test, then your normalized value will be 1, let me put here, 1 minus 8, right? And it will be 0.125. Okay, and then if you get 7 score in your else test, then the normalize the value of your else, result will be 0.875, right? So something like this. And if you got the full score, then the result of your normalized score will be 1. So something like this. This is called normalization, okay? It's called normalization. So this is how to spell else? It doesn't matter. Okay, I'll not put it. Okay, so this is how we use this min max scalar. Okay, so actually this means 8 minus 8. Find how to spell else. Sorry, I forgot about this. IELTS. Right? IELTS. IELTS. E.g., for example. Yeah. So this is how we do normalization. Right? Okay. And then we need to fit this scalar with the features. Okay. So in the file, we have 11 columns. Now we have 11 columns. One of them is the target. But we will not normalize the target. So we need to drop this target. Okay, the target should be the class. It's not numbers. Okay, it's 0 and 1. So we don't normalize the class. The class should be sustained as 0 and 1. So we need to drop this class when we do this normalization. DROP, drop. And we use the name of the class to drop it. Target, target class. It's the name of the class, right? Target class. Okay, and then the column should be the direction. Okay, the direction should be the column, the dropping direction axis. Okay, so the axis, one axis is 0, it means the rows. And one axis is 1, it means the columns. We drop the columns here. Okay. Yeah, so we feed the data, we feed all the features, we apply this scalar to all the features except the target column. Yeah, and then we do this scaling. Okay. Yeah, again, we do the scaling on this part of data. Yeah, so here, when we're using fit, we're calculating the factors, the scalar factors for the data. And then after we got the factors, we normalize the features with these factors. So, but when we're doing normalization or when we are calculating factors of the scalar, the data part we use are all the thing. It's the part of data without this target class, which means all the features in the table. Okay, and then here we got the scaled features. And then we just need to get the new data with the scaled features. Scaled features. Yeah, scaled features. We transfer it into another data frame. Okay. Okay. Then we print the head. So these are the normalized value of the features. Okay. So this is a data frame of the features. And this is a normalized value of the features. So here the columns means we don't use the last column here. Okay. Yeah. In total, we have 10 features here. These are the training data we are going to use for the KNN. Okay, so this is how we do normalization. Normalize the features or variables. Better to see features. Okay, then the same as what we did before. We need to do this train test split to split the train dataset and the validation dataset. Okay. And which dataset we need to use. So we need to scale the, oh no, we use the scaled features. Scaled features. Okay, this is the X. And the Y should be the target of the original data frame. The original data frame is this DF. Okay, we need to use the column of this target class. All right, let's check. Target. Oh, sorry. Okay. And then we need to define the test size. So usually, as I've talked about it in the lecture, usually the size should be 0.7, 0.3, okay? So the test size should be 0.3, like 30% of the data will be used for validation and 70% of the data will be used for training. So this is a common practice for this train test split. And you can also decrease the value, okay, it doesn't matter. But if you you can increase also a bit, but don't increase too much. You should make sure that you have enough training data to have better performance. Okay. Okay, then we define the KNN classifier. So it is called K neighbors classifier. And this classifier is imported from this sklearn library, okay? So all the machine learning method we are talking about from, till now, are all from this sklearn library that we introduced in the previous lab. And the KNN, K nearest neighbor, is called the K neighbors classifier in this library. Okay, so this is how they define the name of this classifier. K neighbors classifier. And then again, we just need to fit this model. So we've already instantiate the model. Then we feed this instantiation, which is called KNN. We feed it with the data we have here, the string xstring. Feed here xstring and y string. Okay. And then we get some predicted value with the X test. Just copy paste from the variables here. Okay. So then we run it. So in this procedure, we train the KNN and then predict the value for Y test with the X test data based on this predict method from the KNN that we trained. Okay, and these are the predicted value. Okay, then we can evaluate the model. Oh, sorry. I forgot to define the number of neighbors. You can define your number of neighbors, the key value, okay, here. Let's say we use 1 first. Okay, so here is the parameter, the hyperparameter of the k nearest neighbors method, okay? And let's first define it as 1. K neighbor, so it means the k value of the KN is 1. One nearest neighbor, we only use one nearest neighbor to decide which class the data belongs to. Okay, we run it again, and then we print the confusion matrix. So there's also a function called confusion matrix. I can just copy paste from here. Yeah, so the classification, as I introduced last lab. Okay, so the evaluation method is also included in this sklearn library. So it is in the sklearn matrix, performance matrix, sklearn matrix. From this library, we import some method, which is called classification report and confusion matrix. Okay, and then we directly use this confusion matrix method to plot the confusion matrix. So when we are doing confusion matrix, we mean the confusion between this Y test, sorry, Y test and predict value. So this is ground truth. The Y test is the label we have in the validation data set, and the predict is the data we predicted by the classifier here. Okay, so we plot the confusion matrix. Okay, so here's the confusion matrix. Yeah, it's a kind of abstract. 有点抽象。然后 let me, where's the lecture? This is our lecture, right? We have confusion matrix here. Yeah. So we have the confusion matrix here. Okay. We can understand these two or these 4 numbers. Right. You can understand these 4 numbers based on the table here. Okay. So the first number, 141, is the true positive. Oh, sorry, true negative. True negative. And then this is the true positive. So these are the correct classifications. And this is the incorrect classifications, which is false. Okay. And then one of them is false positive. One of them is false negative. Okay. So it's like in total we've using 300 samples for test. Okay. And then we made some mistake in 24 samples, and 17 samples are misclassified as as positive or negative, as as positive. And then 7 samples are misclassified as negative. Okay, so these are the misclassification we have. In total, we made mistakes in 24 samples. So this is confusion matrix. And then we can use this report, classification report, which will give you more details about the results. Okay. So again, we use this Y test and Y and the predict. Let's copy paste here. And then it will show you the classification report. It will directly give you all these performance metrics, like the precision, recall, F1 score, support. Yeah. So this is the number of samples, and these are the precision, recall, F1 score rate. Okay. And this F1 score, right? F1 score, we are going. Yeah. So F1 score we've explained here. Okay, F1 score is like the balance, measure the balance between the precision and the recall rate. So if you still remember that we've talked in the previous lecture that we need to keep a balance of this. It's called a precision and the recall trade-off, right? And sometimes you are quite lazy. You don't want to find this trade-off by yourself. And then there's another matrix called F1 score that directly you can use. So it measures the balance between the precision and the recall rate. And the F1 score is calculated as this formula, okay? It's very simple. This formula, 2 multiplied by precision, multiplied by recall, and then over precision plus recall. So this is how the F1 score measures. This classification report. So we can see we have quite good precision and recall rate. Yeah, because the data set is quite easy. Okay, then we've already evaluated the model for the parameter of K, K1. Then we need to try other K values, okay? Let's try the K values from 1 to 40. So previous we already tried 1, right? We define increment of, which is I, okay? And then we put I here. So we put a loop here, K neighbors. So neighbors equal to I. So in every loop, in each loop, we will increase the I by 1. And it will increase from 1 to 39, I think. Okay. And then we do the same thing, fit here. Fit the X string and Y string. Feed the training data here. And then we predict by the test data X test. Okay. And then we just put the accuracy into this matrix that we put here. Okay, we save all the accuracy inside for these 40 iterations. We save all the accuracy in this error rate matrix. Okay, and then we can calculate this accuracy by a very simple method here. I will explain to you later. Okay. I not equal to Y test. Yeah. So here, when we are comparing this predicted value and the y value, okay? So this is a vector, okay? So it has a lot of elements inside. And this is also a vector, okay? So because we have 300 samples for the test, right? So both of them will be 300 values inside. So we compare each value, and if they are not equal, then it will return 0. And then if they are equal, then it will return. If they are not equal, it will return 1, and if they are equal, it will return 0. Then according to the number of 1, which means they are not equal, or which means the error, then we can get the total number of error, and then we calculate the mean value of them. So we got the error rate. Yeah, so this is the error rate. Sorry, this is not the accuracy, it's the error rate. Error rate. Okay, as I put here, it is error rate. We just check how many errors we have here. And we check the error by comparing the result of predicted value and true value. Okay, we get number of errors, and then we calculate the mean of it. Then we call the mean based on the number of samples. Then we get the error rate. Okay, then here is just something about the matplotlib. Then that's how we plot this data out. Okay, we just run it. Then we will see here. So here's the error rate, and here is the value of key. In total, we only tested like 39, I think. So this is checked error rate from K1 to K40. Okay, I think we need to put 41 here. Oh, then the ship is not correct. Yeah, 41. Yeah, then we also have another data point right here. Yeah, so we have 40 data points here. It doesn't matter. Okay, if you put 40, it's also okay. I will not regard that. I will not treat you as wrong. Okay, if you put 40 here. Actually, you can put any value here. And then we can see when we increase the key value from 1 to, let's say, maybe 6 or 7, that is a huge decrease of the error. And then it's kind of stable here. And when we increase the key value again, the error decrease again. So according to this plotting, we can see like the minimum error occurs when the key value equal to something around 26 or 27, right? But this is a kind of vibration here. So maybe you can also just use this value here. Like you can set the key value as 1, 2, 3, 4, 5, 6. And the classifier has already have a very good performance. Okay. So but this depend on data. You can use more data because here is a quite big vibration in this error rate. Okay, it's not a very smooth line here. But you can see when we decrease at the beginning, when we increase the key value at the beginning, there's a prominent decrease in the error. Okay, then we again get the confusion matrix. Is key equal to what? Let's set as 3. right? Okay, so when we set the key value as 3, we can have another report of the result. And we can see now we have precision of 0.96% and 93%, right? So this is the precision for different classes, okay? So like we have 2 classes here. The precision of the first class here is 96 and 93. And then let's say here, when we have key value of 1, the precision is 95 and 89. So we've increased the recall rate by 4% if we just change the key value to 3. Okay, sorry, this should be 3. Okay, this with key equal to 3, and we have better values. We can try like 26, right? 26. Yeah, so it also increased some more, okay? So according to this plot, the optimal value of the key should be like 26 or 28, something like this, okay? But you can get the optimal result for this test set, but you cannot, I'm not sure if you change another test set, it will still have a very good result when we are using key value as 26. But according to the test set we are using now, the best value of key is 26 or 28. And we have the best results here, which is 97, 95. Okay. And when we compared with the previous result here we have 8% increase in this recall rate, and also 2% in the precision for this class 0. And also for class 1, we don't have very obvious we increase also 5% of the precision for class 1 according to the result from key equal to 1. Okay. So this is how you tune these hyperparameters. Yeah, so here I already put, so it doesn't matter. Here's 30, doesn't matter. Let's put 26. 26. So for a faster comparison, okay. And here we use 1. We can put 1 here. Doesn't matter. Okay, so we just put these 2 reports together to have a better view of these 2 reports. So you can compare easily to see the difference between the 2 reports and then to decide the parameter. Okay, so the last thing is about the confusion matrix. Okay, and actually, so all the confusion matrix we are talking about, we only have like 2 classes, but for 3 classes, it's the same. Okay. So here we have 3 different classes, 1, 0, 1, and 2. I just put the sorry. Copy paste the 2 values here, the 2 vectors here. So there's another confusion matrix which has 3 rows and 3 columns because we have 3 different classes. Okay, so if we are doing classification of cat, ant, and bird, so then the result will be something like this. Similar things, okay? So this also shows you how the predict result are confused with the true result, okay? So the values here are the correct values, are the correct predictions. And all other values are the mistake it made. So here it made a mistake. And also here there's a mistake. 1, 2, 3, 4, 5, 6. We have 6 samples and 4 samples are correctly classified. 2 samples are misclassified as different things. Okay, so this is another example of confusion matrix. Here is part 2 for you to finish, but there are no coding assignment here, I think. Just some simple questions, single choice questions for reference. Okay. Yeah, so there's still 5 minutes left. And if you have any problem, please just let me know. Yeah, so one thing I forgot to mention here, okay? So when you are doing the train test split, it is random. So we have, actually your result should be different with mine, okay? So when you are using this train test split, it randomly choose 30% of the data set. So your result, if your result is different with mine, then there's no problem, okay? So that's why I said that in my case, maybe 26 is the best, but for you, maybe a bit different. So don't worry, there'll be no problem, okay? Okay, so if there are no other questions, then it's the end of this class. Thank you very much and see you next week.